All right, well, good afternoon and welcome to my 7 millionth attempt at doing Chapter 3A, Sound Difficulties. Yipes. Anyways, to get right to it, we're starting a new chapter. So like all new chapters, there's a couple of things I want you to remember. The first is, here's the new reading list. This chapter will actually include one section out of Chapter 2. Also, whenever we start a new chapter, there's some optional book problems, which again are great to do if you're struggling on anything we do on homework sets or on anything you may be having some trouble with in class. There's also some learning objectives. Again, these are great as we're moving through the material to kind of keep your eye on the prize. What do you need to know as we're moving through the material? Okay, to get right to it, this chapter is all about elements and atoms. So when we talk about elements and atoms, we have to remind ourselves more generally about matter. So this is out of section 2.1 in your textbook. When we think about matter, which is the stuff that makes up everything, matter comes in two major kinds of forms. One of them is known as pure substances, which is matter that has fixed and definite composition. The other kind of matter is referred to as mixtures, and within mixtures, these are two or more unique substances that can be separated by physical means. What chemists usually care about, at least in the early going, are the different kinds of pure substances, and so chemists are most interested in two kinds of matter. Elements, which are the simplest type of substance displaying unique chemical and physical properties. What we're going to find out here in a minute is that they are not only the simplest type of substance that displays unique chemical and physical properties, but when we're talking about a particular element, each element consists of only one kind of atom, and stay tuned on what we mean by that. The second kind of pure substance I want you to be familiar with are compounds, where compounds are just a combination of two or more elements in a fixed, sometimes referred to as a definite ratio. So if we look at a couple of examples here, water will always be made of 2 parts hydrogen atoms and 1 part oxygen atom. Carbon dioxide is made of 2 elements, 1 carbon and 2 oxygens. Sodium chloride always contains a ratio of 1A for every 1 Cl. So those are compounds, 2 or more elements. Okay, thinking more about mixtures, mixtures come in 2 varieties. Heterogeneous mixtures, which are an uneven distribution of substances. Homogeneous mixtures are a uniform distribution of substances. To kind of tell you a little bit more about what this means, my favorite example of a heterogeneous mixture is a chocolate chip cookie. If we think about a chocolate chip cookie on the molecular level, there's clumps of gooey chocolate chip molecules that are not evenly spread throughout the cookie, whereas, and there's also clumps of cookie dough. But if we contrast that with a homogeneous mixture, where my favorite is Kool-Aid, Kool-Aid on the molecular level has every single sugar molecule infinitely separated away from every other sugar molecule, and it's uniformly distributed throughout water. So whereas heterogeneous mixtures are not uniform, and you can think of there being molecular clumping, a homogeneous mixture does not have any molecular clumping of any one particle. They're evenly separated all the way throughout the mixture. Okay, so those are just sort of an overview of classifying matter. Thinking a little bit more or a lot more about pure substances, specifically elements, elements come in 118 known varieties based on current research by chemists and physicists. Interestingly, it turns out that not all elements occur in nature, and in fact, some elements have been generated or made in the laboratory by chemists and physicists. So what I'd like you to think about just for a second is, why is that true? Why do not all elements occur in nature? After thinking about it for a second, you'll probably eventually come up with some form of the following idea. And basically, the short answer is, it turns out that not all elements are stable. So in Chapter 9, we're going to learn about why or why not some elements are not stable, and that's why many elements don't occur in nature. And the term we're going to use to describe elements that are not stable are specifically going to be elements that are radioactive. Now, we do have some elements in nature that exist and are radioactive, but in that case they just are metastable. That is, they can hang around for a certain period of time. Eventually all radioactive elements will decay, and the ones that are very unstable decay so fast that we can't make them so that we can get appreciable amounts in nature. So stay tuned, that'll be the next thing we do in the class after we finish the Chapter 3A packet. Okay, a few more nuggets about elements. I already told you that they're the building blocks of all compounds and molecules, so no matter what kind of compound we're talking about, it's always made by a combination of two or more elements. Elements, as you guys probably already know, are made from all sorts of goofy, the names are derived from goofy histories, so important people, locations, mythological sources, etc. I'm sure it's just a matter of time before there's a Dr. Bob B. Right. Anyways, the one thing I need you to know about elements is that you can represent elements in symbolic form, and most of you have seen that elements are written out as either one or two letter symbols. But here's the thing that I absolutely have to have you know, and that is whenever you write out an elemental symbol, you capitalize the first letter only. So as an example, this element right here, big N little I, stands for nickel. Any chemist worth his salt, ha ha ha, bad pun, would know that big N little I corresponds to nickel. However, some of you might have been tempted to do the very, very sad thing, which is to write big N big I. That would be very sad and cost you points, so that would be very bad, because if I saw that, I wouldn't think nickel, I would think nitrogen, which has the symbol N, and iodine, which has the symbol I. So just by capitalizing and lowercasing the first and second letter respectively leads you to a much different conclusion than if you do it the correct way. So make sure to never, ever, ever, ever capitalize both the first and the second letter. So that's the right way to do that. So that's one thing to know. Okay, so at this point you might be wondering to yourself, is Dr. Bob really going to make me memorize every stinking element on the periodic table? And the short answer is, who in the planet would have you do that? If your high school chemistry teacher made you memorize every single element, that would be terrible. However, I do think as future healthcare professionals, it's useful to have you know or memorize a few of the elements. And so although I'm not a huge fan of memorization, I will agree with your high school chemistry teachers in that I at least want you to know the elements that are part of life. So basically, I need you to know all the elements on this particular slide, and in particular, I need you to know their names and symbols. But I suspect that you probably know most of these already. So I'm sure if you look at Zn, you already know that that's zinc. But I do need you to know everybody that's in both the major percent list as well as the trace elements. So like, for example, this guy right here is silicon, this guy right here is vanadium, and so on. So I need you to know all the elements that are associated with living things, names and symbols. Alright, the one thing I don't want you to worry about so much for today is how the elements are organized on the periodic table. I do need you to know that the periodic table is a simplified way of organizing all the elements, but for today all I need you to be aware of is that eventually you'll come to find out that the periodic table is a giant cheat sheet, and next week we will start to get into that in more detail. So that's all I need you to know for section 3.2 for now. Moving right along, so elements, there's a bunch of them. They can be organized on a periodic table. The only other thing I want to tell you right now to kind of talk about the other kind of pure substance is that elements combine to form compounds. We already mentioned that. The new nuggets for right now is to tell you that when we talk about compounds, we can write out how compounds look with a compound formula, which is going to just tell us the ratio of the elements, the constituent elements, and it's going to identify each element by its symbol. So for example, water, The way to write out the formula for water is to say, hey, there are 2 hydrogens for every 1 oxygen, and that would be a compound formula. The only other nugget I need you to know for the moment is to say that the properties and behavior of compounds are not the same. Or actually, let's erase that. What I mean to say here is that the properties and elements are very different from that of compounds. And so, looking at one quick example right here, if we look at sodium in the elemental form, sodium is a soft metal, whereas sodium and sodium chloride is a powder. In terms of their properties, you would never, ever, ever want to eat a hunk of sodium because sodium reacts vigorously with water and would do very, very bad things to you. In contrast, if you eat a little bit of salt, salt dissolves in water, doesn't react with water, and tastes pretty yummy. To give you a health-related example like this one, it turns out that there's an antidepressant medication in use that's often referred to as lithium. Well, lithium metal is very much like sodium. If you swallowed it, it would react very violently with your body, and it would do anything but help you not feel depressed. However, lithium in lithium medication actually comes in the form of a lithium ion in an analogous form to lithium chloride. So elements very different from compounds. Okay, so that's enough about elements and compounds. The next thing we want to talk about is to say, well, we know that elements combine in some sort of way to make compounds, but exactly how do they do that? And to think about that, we next have to talk about something called Dalton's atomic theory, which leads us to the conversation of atoms. And what I want to talk about, at least for a minute now, is to say, why on earth do chemists believe in atoms? And to this point in your life, you probably believe in atoms only because your high school teacher told you so. But like I told you on the first day of class, I don't want you to just go with the told you so argument for why we believe in things. It's always based on scientific experiments and the scientific method. And so atoms are no exception. So what I want to do is to at least give you an overview of 3 fundamental experiments that convince us that atoms really do exist. So, let's go. 2 easy reasons for why we believe in atoms come first. First is called the law of conservation of mass. It turns out that mass is neither created nor destroyed during a chemical reaction. Translation, what that means is that when you do anything, the stuff can't come from nothing and can't go into nothing during a chemical reaction. If that's true, that means we must have globs on some scale, even if it's very small, that's coming together to form the stuff that we form during reactions. So everything must be made out of stuff, matter. The second mass law that helps us to believe in atoms is known as the law of definite composition. And I'm just going to cut to the chase. There's a long-winded message right here that says no matter what you find, where you find a particular substance, that substance will always be composed of the same stuff in the same parts by mass. To put it another way, if I find calcium carbonate, which is what this species is right here in the United States, if I find it in India, South Africa, Saudi Arabia, Canada, no matter where you find it, calcium carbonate is calcium carbonate is calcium carbonate. All calcium carbonate from all sources looks exactly the same. To put that into numerical context, what that means is that if I find 20 grams of calcium carbonate from the United States, or from India, or from Africa, or from Australia, or from wherever, it will always have 8 grams of calcium for every 20 grams of the whole thing, 2.4 grams of carbon for every 20 grams of the whole thing, and 9.6 grams of oxygen for 20 grams of the whole thing. If I express that in either a fractional form or in percentages, it will also say the same thing. If I have 100% of a dollop of calcium carbonate, based on this mass ratio right here, 8 out of 20 times 100% is 40% calcium. Calcium carbonate from the US, from everywhere, is always going to be 40% calcium. It's going to be 12% carbon and 48% oxygen. So not only is a compound made out of particular elements, if I have a particular compound, it always has all the same parts in the same mass fractions, the same mass percentages. So 2 reasons why we can believe in atoms. The third reason is probably the most important reason, but it's unfortunately the more confusing law, and that's known as the law of multiple proportions. And so to work through this, I'm going to work through example. So the statement of the law of multiple proportions goes like this. If I give you a compound that's made of 2 elements, an element A and an element B, and they react to form 2 different compounds, if you take the different masses of B that contain with the fixed mass of A, you can express the ratio of these different compounds in small whole numbers. Let's show you how it looks. So suppose we have 2 carbon-oxygen compounds known as carbon-oxygen oxide compound 1 and carbon-oxide compound 2. Now both of these carbon-oxygen compounds are made of 2 elements, oxygen and carbon. If we look at the carbon oxide compound 1, here's what we see. The ratio of the mass of oxygen for the mass of carbon is going to be equal to the ratio of 57.1% divided by 42.9%. 57.19 grams of oxygen for every 42.9 grams of carbon. If you take that ratio, here's what you find out. 1.33. Guess what? By itself, that doesn't mean a darn thing. However, if we look at the same mass ratio for the second carbon-oxygen compound, which is boxed in yellow over here, and we take the ratio, we see that the grams of oxygen to grams of carbon ratio in this compound is a little bit different. For every 72.7% or 72.7 grams of oxygen in this compound, there's 27.3 grams of carbon. If we take the ratio here, the ratio works out to 2.66, which also means nothing. However, according to the law of multiple proportions, if we take the ratio of ratios, 2.66 divided by 1.33, something really cool happens. If you take the big one over the small ratio, check out what you get. You always get a ratio of a whole number. In this case, it happens to be a 2. Here's why this is so neat. What this is saying is that if I take a glop of carbon will only make compounds with glops of oxygen in very particular ratios. I can only add new dollops of oxygen on in discrete plops. 1 plop at a time. And by taking the ratio, the ratio of ratios, this is how I can see this. Glops of oxygen get added to carbon 1 at a time. That's the law of definite proportions. And someone really smart came along and said, hey, if this is true and those first 2 mass laws are true, you can come up with a model that says that matter can only be made of indivisible hunks of stuff, which we're going to call atoms. So Dalton's postulates, or Dalton's atomic theory, says that all matter consists of indivisible nuggets called atoms. His postulates were all atoms are made of atoms. According to these 3 mass laws, atoms of one element, based on the law of definite proportions, cannot simply be converted into an atom of another element by a chemical process. If that were true, then if you mix carbon and oxygen, you might get out some sort of random mixture, which doesn't happen. Postulate 3, according to Dalton, says that atoms of an element are identical in mass and other properties and are different from atoms of any other element, which is why we see the ratios and the proportions that we do. The 4th postulate is probably, again, the most important postulate of atomic theory, and that says that compounds result from different combinations of a specific ratio of atoms of different elements. And that's why we can write compounds that have the very nice, neat, and tidy formulas that we do. This is a Dalton's atomic theory, and although I don't need you to really worry about the individual postulates, I basically want you to get the idea that atoms come in hunks that can be put together in whole number hunk ratios. To show how this all works in an evidential point of view, let's look at one simple reaction right here shown in this atomic model. On the left side of our reaction, we have two compounds. We have a compound called methane, which is made of 1 carbon atom and 4 hydrogen atoms. 1 part carbon for every 4 part hydrogen. We have a second compound of 2 oxygen atoms hooked together, which we call molecular oxygen. There are 2 molecules of oxygen. If we react these two things together and we look at the compounds that result upon reaction between those elements, what we find is that on the right side we have 2 new compounds, a molecule of carbon dioxide and 2 molecules of water. But if we add up the different elements that form these compounds, we see that all atoms are accounted for. On the left side we have 4 oxygen atoms, on the right side we have 4 oxygen atoms. On the left side we have 1 carbon atom, on the right side we have 1 carbon atom. 4 hydrogens on the left, 4 hydrogens on the right. So by Dalton's atomic theory, we can determine or account for all of the mass on both the left side and the right side of the equation by a simple rearrangement of the nuggets. So that is Dalton's atomic theory in the nutshell. Okay. And by the way, we're going to do a cool lab on this next week. All right. So at this point in time, we're going to pause for a second. We're going to say the following. What Dalton said is he can account for compounds and elements based on indivisible hunks of matter called atoms. Now after Dalton, it turns out there's some more work that's actually found that we can break atoms down into subatomic particles, but when we break atoms apart into subatomic particles, they're going to lose their individual identity as elements. So we haven't violated what Dalton said, but it turns out that atoms can be broken into smaller parts. And you guys already know what these are. So let's just quick review. Atoms are made of 3 subatomic particles, which we call protons, neutrons, and electrons. Now, what do you already know about protons? You already know that protons are going to be subatomic particles that have a positive 1 relative charge. Electrons are going to be subatomic particles that have a negative 1 positive charge, or negative 1 charge, and then neutrons are going to be neutral. Before I move on to tell you about where these subatomic particles are in atoms, I do want to say one important thing about subatomic particles in general, and that is the most important thing I need you to know about chemistry, and that is the following. All of chemistry to a first approximation can be explained by this rule right here, and that is opposites attract plus likes minus. When you're on a Gen Chem exam and you forget what is accounting for what we're talking about, chances are chemistry can be explained by saying plus likes minus. So this is really important. Remember this rule right here. So plus likes minus. The other thing to remind you of is that if opposites attract, that means like dudes don't like each other. Positives repel, negatives repel. And we'll talk a little bit more about this in a moment. Now thinking about atoms, or coming back to the atom, here's an interesting nugget. All elements are made of a particular kind of atom. But here's the interesting thing. Although atoms of all elements are made of these same three subatomic particles, it turns out that every property of a particular kind of atom actually depends on the properties of each atom are unique and only depend on the number of subatomic particles that each element contains. So it turns out that taking different amounts of these subatomic particles give rise to all of the different elements that we have in front of us. So that's kind of interesting, and now we're ready to move on to saying how is an atom put together. So where the heck are all these subatomic particles? And I'm going to cut to the chase for right now because we want to just kind of give you the results, and we'll eventually come back to some of the details. So let's talk about things you know. Where are the protons and neutrons in an atom? I bet you already know that protons and neutrons occupy a dense nucleus. So in our typical cartoon of the atom, which is shown here, if you can represent an atom as a big giant sphere, the protons and neutrons are in this very, very small nucleus right in the middle. Now this picture is terrible in that it's not to scale. If we look at the diameter of a nucleus, it's 10 to the minus 15 meters compared to the atomic diameter, which is 10 to the minus 10. So if we drew this to scale, the nucleus would actually be 1/10,000th the size of the atom. So it should really be in a very, very tiny little small dot where that's still way too big. But that's where the protons and the neutrons go. What about the electrons? Well, electrons, as you can see in the picture over here, represent the cloud around the nucleus, and so we say they effectively represent the large empty space around the nucleus. And this is pretty goofy, and this is one of the modern pieces of how we came to understand chemistry. It was around the turn of the 20th century, so in the 1900s thereabouts. And what I'm going to tell you for right now is that I promise decades, literally, of experimental research support this, and I want you to take this model to the bank. Protons and neutrons in the middle, electrons on the outside. But I do want us to think about this for another couple of seconds, because there's a couple of things that we just got done saying that should make you feel a little uneasy about this model, even though I'm promising that it's true. So let's talk about the unsettling features, the oddities, if you will. So the first oddity goes like this. I just got done telling you that all the protons go in this very dense nucleus in the middle. But protons are made of positive charges. How the heck can you shove tons and tons of protons into a very, 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 very small space if they don't like each other? Now, after thinking about it a little bit, here's an answer that will satisfy for Chem 111, although a physicist probably would cringe at this explanation. And the short answer is, the reason they can cram into such a small space is because there's neutrons there too. And so it turns out a neutrons you can sort of think as a nuclear glue that holds the nucleus together. And probably a more useful way to think about neutrons is that they sort of buffer the positively charged protons away from each other. To kind of think about this in a picture sense, if I have two protons that don't like each other, how do you keep guys that don't like each other from, hurting each other? You put a buffer or something in between them, and so the buffer, as it were, in the nucleus is the neutron. Now that's really not a great answer from a physicist's point of view, and I want to at least give you a word that does slightly better than that. It turns out we can describe this glue in a better definition as the strong nuclear force, and this is one of the four fundamental forces that physicists talk about. So the strong nuclear force. What you really need to know is that the strong nuclear force of the four fundamental forces is much, much stronger than the plus likes minus or plus doesn't like plus force. And so the reason nuclei don't freak out to a first approximation is because when you put protons and neutrons together, they're glued together by this fundamental force known as the strong nuclear force. And we'll come back to this when we start talking about why certain atoms are radioactive. But for right now, that's good enough. Okay, so that's oddity number one. Oddity number two, electrons. They're negatively charged particles. Why the heck don't those negatively charged particles crash into the nucleus? Okay, why don't they just fall? They like positive, so why don't they just fall into the nucleus? The bottom line is, it turns out it has to do with a couple of weird behaviors of things that are really, really small, which electrons are, very, very small mass, and things that are moving really, really fast. In fact, so fast that they're moving at speeds near or approaching the speed of light. Now, you guys know that when things approach the speed of light, they're governed by that, or Einstein was the guy that figured out how this stuff all worked, and whenever you start talking about Einstein-related things, it's going to get a little strange. And basically, that's the short answer I'm going to give you. If electrons are moving really, really, really fast, near the speed of light, we can't think about them as particles that act in a normal particle-like way. A negative particle would want to crash into the nucleus because a negative particle does like a positive particle. And that's still true. Plus likes minus. However, when we think about them as waves, they can't be imagined as falling into the nucleus, and they're best described with a form of mathematics known as wave mechanics, and they're described by wave-like properties. And when you start describing particles with waves, their behavior gets really, really weird. And I will actually talk a little bit more about this in Chapter 3B, which we'll get back into after we finish the nuclear chemistry chapter. For right now, it's sufficient to know that it's weird because of this Einstein-like behavior. So that's it for now. So stay tuned. Okay. So to summarize, where are we at so far? We talked about elements, we talked about atoms, we talked about compounds. Summarizing what I need you to know about atoms is that atoms are made of 3 subatomic particles, protons, protons, electrons, and neutrons. I need you to know that protons are plus, electrons are minus, neutrons are neutral. They live either in, outside of, or in the nucleus respectively. And the other thing I need you to know is what their masses are. So a proton weighs, no, I don't need you to know what the mass of a proton is to 4 significant figures or 5 significant figures and with weird numbers. I do want you to know the relative mass of a proton, electron, and neutron so far. And it turns out whenever a chemist deals with a really ugly number, these are very ugly numbers, we like to come up with a new kind of way of describing them that looks pretty. And so we define a convention where we take the masses of protons, electrons, and neutrons, and we redefine a mass in the form of something called the atomic mass unit. It turns out that 1 atomic mass unit is going to be meaning the same thing as 1.66 times 10 to the minus 24 grams. In other words, if we define an atomic mass unit like this, a proton in terms of atomic mass unit scale, instead of calling it grams, calling it AMU, weighs about 1 AMU. Let's change to green so you can see that. So a proton weighs about 1 atomic mass unit. A neutron weighs about 1 atomic mass unit. An electron weighs about 0 atomic mass units. And so when we're keeping straight what accounts for the mass of atoms, it's essentially the protons and the neutrons. And that will be very helpful for us moving forward with a few other definitions on keeping or highlighting how we can summarize how atoms of a particular element look. And so the last thing to do in our webcast today is to talk about identifying particular elements and the parts that make them up. So we're just going to give you a few definitions that I do need you to know. First definition for deciding how many protons an atom has is that it turns out that all elements of a particular element will always have the same number of protons. And it's so important that we say that the number of protons of an atom is also called the atomic number, which is sometimes denoted with the symbol Z. Z means atomic number. The atomic number of an atom, which is the number of protons, is sufficient to uniquely identify a particular element. So the element that has the atomic number 11 will always be an atom of sodium. If we look at the periodic table, every single atom can be determined by its atomic number. So somebody like carbon always has the atomic number 6. 6 protons. Helium always has 2 protons. So the atomic number is really important. The number of protons determines the identity of an atom, and when you look at every periodic table everywhere, it will always minimally list both the atomic number and the elemental symbol. The reason we list both, or use symbols rather than just a number, is because it's a lot easier for us to distinguish boron versus carbon with a B and a C rather than saying, oh, element 5 versus element 6. So we want to list both. Okay. So that's the number of protons in an atom. What about the number of electrons? Well, I just got done telling you guys a few minutes ago that nature often tends to turn out to try to come out with the idea that plus likes minus. To put it another way, all of nature tends to try to find a way to become electrically neutral. That is, when something is electrically neutral, it has a net charge of 0. And an element is electrically neutral. So, what does that mean in terms of elementary particles, the subatomic particles? An atom must always have an equal number of protons and electrons. To do an example based off of that, if we think about an atom of aluminum will always have 13 protons. To be a neutral atom of aluminum, it dang well better have 13 electrons too, so that the charge adds up to 0. Just to show you how this works with a little math equation, if each proton is plus 1, and there are 13 protons, the total positive charge of an aluminum nucleus is plus 13. If an atom of aluminum has 13 electrons, where each electron is minus 1 and there are 13, that's a total of minus 13 charges. If you add up the proton charge and the electron charge, that is what I mean when I say it's neutral overall. The pluses cancel out the negatives when you add them together. So atoms are electrically neutral. The last definition I need you to know something about is called the mass number. The mass number is simply the number of protons plus the number of neutrons in the nucleus of an atom, of a particular atom. The reason we call it the mass number is because we just got done telling you that the protons and the neutrons account for almost all of the mass of an atom. So if we count up the mass number, count up the number of protons and the neutrons, we know very quickly what the approximate atomic mass of a particular atom is. And it is a whole number. So the mass number of a carbon atom that has 6 protons and 6 neutrons would be 6 plus 6, which is the same as 12. So the mass number of carbon with 6 protons and 6 neutrons is 12. We can summarize all this information by using something called a nuclear symbol. Your book will sometimes refer to it as an atomic symbol. A nuclear symbol is basically a way of summarizing all 3 of the definitions I just gave you. And the easiest way to show you how it works is through example. If I give you an atom of sodium that has an atomic number 11 and mass number 23, we can write out its nuclear, aka its atomic symbol, as follows. First of all, we're going to write out its elemental symbol, which is Na. The right way to write out its atomic symbol, its nuclear symbol, is to write the sodium atomic number in the lower left corner, which is again the atomic number, and we'll write out the mass number in the upper left corner. So that's the mass number. So if I ask you to write out a nuclear symbol, this is what I mean. Mass number goes on top, so the bigger number goes on top. On the left side, the smaller number, which is the atomic number, goes on the bottom. So the way I keep them straight when you write out an atomic symbol is that the big number goes on top, the little number goes on the bottom. Those are nuclear symbols. And what I want you to be able to do is, if I give you either the protons, neutrons, and electron count, or if I give you the nuclear symbol, can you figure out how many protons, neutrons, and electrons there are? So looking quickly at oxygen, based on our definition, here's the nuclear symbol. According to this, the atomic number is 8, therefore there are 8 protons. If I were to ask you how many neutrons it has, you would say that it has how many? You would say that it has 8 as well, because the mass number is the number of protons plus the number of neutrons. So since we just determined that there are 8 protons, if the mass number is 16, that means that there must be 8 neutrons, so 8 neutrons. Lastly, if we're talking about a neutral atom, if it has 8 protons, it darn well better have 8 electrons. So that would be true for an atom of oxygen with a mass number of 16. Looking at the second example, we have phosphorus. Phosphorus has 15 protons according to the atomic number, If it has 15 protons, it better have 15 electrons because it's electrically neutral as an atom. What is the number of neutrons in this case? If you said 16, you would be correct because, again, 31 is the protons plus the neutrons. So if we have 15 protons, 15 from 31 is 16. If we do one more example, this is zinc. According to this table, zinc will have an atomic number of 30, so 30 protons, 30 electrons, and it would have 35 neutrons. So this will be the easiest 5 points you'll ever get on an exam if you can remember that atomic number is the lower left, mass number is the upper left, and then electrons are equal to protons. And with that, we'll say that we've done enough for a webcast today. I'd like to say have a great day, and we'll see you in class. All right, bye-bye.